Thank you for joining us today. We know you're busy and we're flattered that you've chosen to spend the next 45 to 60 minutes with us. The title of our webinar today is Graph Data Science with Knowledge Graph Embeddings, and we hope you'll find it interesting and informative. Next slide.
All right.
With that, let me hand it over to Parker.
Thank you. So I'm Parker Erickson. A little bit about me. I'm currently a senior at the University of Minnesota, pursuing a bachelor's and a master's in computer science, creator of the PyTigerGraph Python package. And I am a part-time software engineer at Optum, where I have spent a lot of time experimenting with different graph machine learning techniques, and one of those being graph machine learning for fraud detection, which is currently in the patenting process. And feel free to reach out. I'll have my LinkedIn and my email at the end of the presentation too, but there's the my bio. So sort of going into the agenda for today. First, we're going to talk about what I term graph plus machine learning, and then we're going to go into graph machine learning. So what I consider graph plus machine learning is using TigerGraph or your other graph databases to extract features. You get the benefits of no joins. You get the benefits of maybe being able to run some traditional graph algorithms like community finding or page rank, and using those as features into your more traditional tabular machine learning models. We'll move into then graph machine learning, which really takes its form when the structure of your data and the relationship between your data matters. We'll talk about graph neural networks, and then an intro to embeddings, and finally knowledge graph embeddings with some demo code, and then just start to wrap up some design considerations, decisions to be made when you are thinking about using machine learning with your graph database, TigerGraph, etc. So moving into graph plus machine learning. So graph can accelerate a lot of traditional machine learning workflows because of the lack of joins. So instead of combining 24 different tables in your database together, or maybe needing a table from this database and then needing to connect to a different database somewhere else and joining those, TigerGraph allows for easy, one source of data, pull it out of the database and start working on your models. So that doesn't really speed up the accuracy or the inference of your models, but it certainly speeds the development time, which is very powerful in its own. We can also use knowledge graphs to enrich outputs of ML algorithms. We can, maybe run some sentiment analysis on some documents that we have linked together in our knowledge graph. We can also find entities and how they relate to one another with NLP, and then move those entities into our knowledge graph. And then, like I mentioned before, also perform feature engineering with graph-graded attributes such as community finding, page rank, etc. Those things can go into your traditional machine learning algorithms like random forests, XGBoost, things like that. So just sort of to lay out this process visually, you start with your graph data, you write some GSQL queries to create features or just extract features. You make your REST request, or you connect it up to Spark, or however you want to extract your data. But that's in a table, so you go ahead and run your random forests, XGBoosts, things like that. And then you have your model results and predictions, which you can either share with stakeholders and or you can actually then put those predictions back into the graph for later use. That's a pretty conventional machine learning workflow in general, except using a graph instead of your traditional relational systems. But where this sort of breaks down is when the structure of your data matters. And there's a couple different use cases that come to mind. Something like money laundering networks, or recommendation systems, or social networks, where, LinkedIn is a wonderful example. You have, I might be connected to John, John might be connected to Dan, and we'll try and predict if I am connected to Dan because of the shared link that we have with John. So those types of problems are wonderful for graph machine learning techniques, such as graph embeddings and graph neural networks. We could also, incorporate some amount of graph information by combining those classical graph algorithms, such as community detection, page ranks, things like that, and move those features into our more traditional machine learning. But we'll move then into our graph neural networks. And so graph neural networks are relatively new, just about the past 3 to 5 years or so. One of the landmark papers is Graph Convolutional Neural Networks for Summer Supervised Classification by Kip van Welling in 2017. And then we also have graph attention networks, which are actually, turns out, a general form of transformers from natural language processing, which is sort of interesting. But the way that these graph neural networks work is that it relies on something called message passing. And so let's say that I want to make a classification for node A, and I have a 2-layer neural network. So the first layer will be looking at the neighbors of vertex A. So we'll look at A itself because that's a neighbor of D. We'll look at F and E as neighbors of C, and we'll look at A and C as neighbors of B. So you can sort of see this laid out in this diagram, where our D, or our blue vertex, is shared, known as a message. We're sharing information from A and incorporating that into the message that we'll send from vertex D, or the blue vertex. And then for like vertex C, we'll combine A, B, F, and E. All that data, usually it's like, if these were documents, it would be like a TF IDF vector of the word instances or something like that. And we'll do some aggregation of those vectors. Sometimes it's a maximum, sometimes it's a sum, sometimes it's an average. It's sort of up to you to decide, but that forms a message. And that message is then passed on to the next vertex in your layer system, where that's incorporated with its own features. So you incorporate all of the neighbors, you aggregate them together, you add the feature of that vertex that its neighbors are, and then you pass that along to the next layer. So you can see that the classification for A relies on the message from D, C, and B, and those messages rely upon the aggregation of those neighbors' messages. And now, the drawback to this is that it relies upon having the entire adjacency matrix for the graph in memory. And so, once you get above 10,000 vertices or something like that, it's really hard to find machines that can compute all of these messages and keep it all in memory. And there are some Python packages that are introducing graph neural networks. PyTorch Geometric and DGL are the main two. But they really haven't expanded to parallelized across multiple machines yet. And so you're sort of limited with your memory constraints on the size of the graph that you can do. Sometimes you can perform neighborhood sampling to try and scale, but these techniques are sort of on the fringes of the current academic literature. So then we get into embeddings. And before I really start with what embeddings are, I want to think about why we would want to use them. So embeddings convert sparse vectors into dense vectors. So sparse vectors might be just like, let's say you have 10,000 elements and 10 of them have a 1 in a spot and the rest of them are 0. So there's a ton of memory waste going just to storing zeros. And so what we want to do is think about this is if we had a book that only had a single word on each page, that would be really hard to comprehend if you only had one word on each page. And it would be a terribly inefficient use of paper. Sort of off to the side, the image, we'd have a book that's 5 times thicker or 10 times or even 100 times thicker than just what we would have if we printed a book like we'd normally print a book. And so this is the same issue with using sparse vectors for machine learning tasks, is that if you have, an important word every 100 pages, it would be very hard for an algorithm to pick out any meaningful patterns or predictions out of that vector. And so if you have a knowledge graph with, let's say, 1 million vertices, and you want to represent what each vertex is connected to with an edge, you would have a 1 million dimensional vector of all zeros, except for maybe the 5 to 20 different relationships that one vector has with other vectors. And that's really an inefficient use of memory, and it's a really inefficient way to try and have a machine learning algorithm understand what you're trying to represent. And so embeddings are low dimensional numerical representations of data. So you can sort of think about reducing each data point, be it a vertex in a graph or a word or what have you, into a point on an XY grid. You could have it to be 3D, 4D, 200 dimensions if you're compressing what you're representing into a smaller dimension. So at the most extreme, you could compress it down into 2 dimensions. And this is sort of the example that I go with, is if we do the vector for king and we subtract the vector for man, we end up with the representation of the vector for queen. And you can sort of see this visually in this 2D space. So it's really at its deepest level, it's just trying to reduce dimensions and make it more understandable both for humans and for machines. These embeddings can be used for inputs into machine learning models such as NLP tasks. BERT is huge right now. GPT is huge right now. And those both use word embeddings to represent data inside of their models. Anomaly detection, so you can cluster things into lower dimensions, and if there's some outliers, that might be a sign that those instances are fraud or something along those lines. And then you could also just use it as an input vector into regression or classification tasks, like you would with any other machine learning model. You could also do distance calculations between data points, which is sort of what got me down this road with my work at Optum, is that we want to figure out how to compare patients and determine how similar they are in order to recommend certain, care paths or medications or things like that. And so now we'll sort of move into the knowledge graph embedding specifically. And these knowledge graph embeddings basically reduce what I was describing before, an adjacency vector, where if you have 1 million vertices in your graph, we want to reduce that number from 1 million to maybe 200 or something along those lines. So we reduce the amount of memory needed, and we compress the information into something that's much more manageable and understandable for machine learning tasks, distance calculations, things like that. And so there's sort of two standard ways of generating embeddings as far as graphs right now. One is node-to-vec, and node-to-vec works with random walks in your graph, which form sentences of vertices. So imagine that you start at like a patient in a knowledge graph, and you might take one step and you end up with a diagnosis code for hypertension. And then you take another step and you end up with another patient that also has hypertension. And then you take another step and that patient also has an allergy for this. By recording those walks from patient to diagnosis code to patient to allergy to medication to whatever, we can actually then use those recordings of the path that those took to sort of understand the probability of reaching each vertex given the vertices that came before it. And this is, these walks are used in a skipgram model, which is word-to-vec. So we truly treat these random walks as sentences and vertices as words in node-to-vec. The problem is that a lot of that doesn't scale. So you might have 1 million vertices in your graph. If you have, typically you do random walks of 20 or longer, and maybe 20 to 50 walks from each vertex to get an understanding of what is in that vertices neighborhood. So you have, 1 million times 20 times 20. So you have somewhere in the neighborhood of 400 million walks that you need to record on the small end. And that just becomes really impractical, not from even just a storage standpoint, but also from a time to generate all those random walks standpoint. And then we have another class of graph embedding algorithms that are all under, I think they're just knowledge graph embeddings, usually is what you typically see them as. They are all implemented in this package called DGLKE that was developed by AWS. But there's a couple different algorithms. Some of them are TransE, TransR, and Dismal. And these all rely on a list of triples. So you have your head, which is your source vertex, your relation, which is your edge in between, and your tail, which is your destination vertex. So like in TransE, what the goal is to create a vector for the head such that the head plus the relation gets you the tail. And now, obviously, none of these are going to be perfect because, most graphs have vertices that are connected to more than one thing. But approximately, it tries to minimize the distance between the head plus the relation and the tail. And so what this does is brings things that are closely related together and spreads apart things that are distantly related. And TransR and Dismal both do similar things. Dismal, I believe, does like head times relation should equal the tail versus head plus relation should equal the tail. TransR deals with rotations in the vector space. There's just different variations upon what manipulation you are doing. But generally it's the source vertex and you manipulate it based on the relationship type, and that should approximate the destination vertex. And so now we're going to head into the demo here. First, I want to show the schema for the Tiger Graph instance that I'm using. Unfortunately, I don't have Graph Studio up to date just because of the amount of data that I have in this graph, the RAM constraints, especially when using video conferencing, really is tight on my laptop. So I didn't want anything to crash. And so here's a screenshot of the schema. As you can see, we have our patient here. We have some demographic information like race, gender, ethnicity, some geographic information such as address, zip, state, city, things like that. And then we tie everything to SNOMED codes. And these SNOMED codes are entities that are standardized across the medical field, such that, like diabetes has a SNOMED code, hypertension has a SNOMED code, an allergy has a SNOMED code, prescription that you might have has a SNOMED code, things like that. So like here we have a has allergy edge from the patient to a SNOMED code. We also have a condition edge from patient to SNOMED code, immunizations, observations, things like that. And then we also have medication, which is really the prescription record for the patient. So that's tied directly to a patient and becomes its own vertex. But we also keep track of the code that is the reason for this prescription and the drug's SNOMED code itself as well. Same thing with like imaging studies or procedures. We have both the reason and the procedure code. And so this is, my graph has about 7,500 patients or so. But with the SNOMED codes and visits and things like that, it comes up to about 1 million vertices. So we'll head into the demo here. First, I'll show you briefly the code that I use to load all of this, all written in Python. And this data set is generated with a tool called Cynthia. So it truly just outputs a whole bunch of CSV files that you can read in with pandas or something like that, and then use PyTigerGraph to load them using the REST endpoints in your TigerGraph server. There will make some slides available and the code available after the talk here, if TigerGraph hasn't already done so. But so once all the data is uploaded into the database, we can then extract the data into these triplet edges. So here's the query that I use. And basically what we do is we define a tuple where we keep track of the source vertex, the edge, and the destination. And then we start with any vertex and we select the target as long as it's not a self loop. You could incorporate self loops as well. But in this example, there aren't any, so just wanted to confirm that we didn't have loops. And we just accumulate all the triplets consisting of a source vertex, an edge, and a target vertex. And so what we do is truly pull all of those relationships out of the graph and do some data frame manipulation. And we end up with a data frame with this source, edge, and destination. Let's see if I can pull it up here. Should have had that preloaded, but yeah, so here it is. It's all tab separated. So we can see like took place at is a thing for a visit. So like this would be a visit, took place at a location. This is a SNOMED code, and this patient has this observation, things like that. So with this data frame, we can then feed it into that Python package that I said called DGLKE, and we can define where we want to get our data from, what we want to name it, things like that. Also what model we want to use. So I used distmalt. It was the most promising out that I tested. And then we can also define the hidden dimension, which is the dimension that we want to compress our data down into and form embeddings from. So this process takes a while, but you can go ahead and run that. And then and that saves a NumPy array. And this NumPy array is outputted right here, where each entity has a embedding. And so, no, I lied earlier. We have about 375,000 entities in that graph. And then each of those entities has a vector of length 200 representing it. And we also have relation embeddings, as we mentioned in that PowerPoint deck. And so we can also then look at our relationship embeddings and maybe compare relationships or something like that if you wanted to. I then incorporate these back with the data and do some cosine similarity testing, but then also perform PCA on it. So I have 3 PCA values to further reduce that embedding from 200 dimensions into 3 dimensions. And we can then take a look at this notebook, which loads in the same CSV. And then we can plot those PCA representations. And so we see, this is sort of a busy version, but this is every vertex in the graph is plotted. And so we can see some clusters already, but if we just take a look at patients, you know, this, we see a distinct cluster here, distinct cluster here, distinct cluster here, things like that. And so these patients are going to be more similar to one another within a cluster instead of like a patient in this cluster compared to this cluster. And so we can also then look at SNOMED codes and how they relate to patient clusters. And so like this cluster has a smattering of SNOMED codes inside of it as well. And these patients, if you actually go look at the graph, have these SNOMED codes associated with them. And so it really compresses all that information from the graph from a 375,000 dimensional vertex, or into 375,000 dimensional vector into a vector of 200. And then we can further compress that and look at and analyze our data in 3 dimensions or 2 dimensions. So that's sort of where we are right now as far as embeddings, but these embeddings could be also, you know, one of these, one of the use cases for this is like you pass in 2 different embeddings and you predict if those vertices should have an edge between them. And you could do that with your normal classifier or your with a neural network or something like that, where you concatenate the 2 vertices or vectors that represent the vertices that you want to test. And then you end up with a binary output of, yes, this should have an edge, or no, this shouldn't have an edge. And so we'll head back into the slides now. So this is sort of the grid that I like to think of when sort of thinking about what algorithms should you use when using graph with machine learning. And so if you have static data and you have data that is structurally important, I would tend towards graph embeddings. One of the downsides of graph embeddings is that you have to extract the entire graph to generate these embeddings. So let's say, like in the patient use case, let's say a new patient comes in with, you know, this diagnosis code, and this allergy, and we want to find the most similar patients. We can't just add this patient into the graph and we already can compare things. We would have to truly extract everything again, run this embedding algorithm, which for larger data sets takes more time, and then run it again. And then we can compare things. But graph neural networks, there are ways, if you have dynamic data that is structurally dependent, graph neural networks can work with the subsets of your graph. You can train it to work with time series data. That's sort of an ongoing research area. That's sort of the edge of academia. But then on the other side of things, we have not structure dependent, and that's where graph plus ML really shines. Not everything needs an embedding. Not everything needs a graph neural network, But sometimes just being able to do the feature engineering and the feature extraction that you want to do very easily and efficiently without 24 joins or trying to tie in 5 different database systems, things like that really benefit from graph plus machine learning. And then sort of at the bottom of this grid, we have scalable to the left and explainable to the right. And that really more applies to the upper half of this grid as far as graph embeddings and graph neural networks. Graph embeddings are a little bit more opaque of a model in terms of you don't really have much explanation as far as what numbers it comes up with for the vectors, the vector representations. But graph neural networks, if you're running like classification or something, you know, because of the message passing that goes on, you know how far of a scope that algorithm looked at to classify that vertex. So like if you have a 2-layer graph neural network, you know that the explanation of the classification is within 2 hops of the vertex that you're trying to classify. So it's not really explainable because it still is a neural network, but it gives a little bit more context than the typical just black box neural network. And then you have your graph plus ML choices for explainability, like a decision tree or XGBoost with feature importance scores, things like that, that tend to just be sort of explainable in general. And so, as I sort of touched on throughout the presentation here, further developments, this is sort of what's going on in academia and the papers being published right now. Incorporation of temporal data. So, maybe not just saying, okay, this person had a broken arm 5 years ago, so there's an edge in between this person and a broken arm, but saying, okay, this person had a broken leg literally a week ago, that's more important than a broken arm 5 years ago, probably. So incorporating that temporal aspect of how that importances may fade due to time passing is one aspect that research is going. Also, inductive embedding creation for unseen data. So like trans-E or distal and things are known as transductive algorithms, in the fact that everything that they train on, you can't incorporate a new item into the data set that they train on. So inductive means that you can, have the new patient that walks into a clinic and predict predict their embedding without redoing all of the embeddings. And then we also have predicting embedding trajectory. And so sort of that's represented with a figure on the right here, with if you have edges between your items and your people, you could try and predict based on like the time that each person got interested in the item. You could try and predict the trajectory of where the embedding or that person might be placed in that vector space in the future. And so like going back to the patient example, you might be able to predict, this person has an embedding of this. And so in the future, it might turn into embedding of this, which represents a patient might develop this disease or this condition, things like that. And so some resources here. Oh, somebody wrote up a very good paper on Medium, predictions and hopes for graph machine learning in 2021. Really gives a good overview of where research is now and where it's going. I have some papers on a GitHub IO site. PyTiger graph is well documented. And then the demo repositories are there as well. But you know, we'll get those out to you afterwards. But with that, thank you. I would love to open it up to any questions. I think, John, you are moderating this, correct?
Yeah, so if you have any questions, please put them in the chat now. We do see a few questions that haven't been answered. One of them, I've seen a fair bit of attention on Shapley approaches for explainable of black box models. Could that be applicable to these graph neural nets?
Probably. I'm not hugely familiar with Shapley, but I mean, graph neural networks are neural networks at its core, so I don't see why not. There's also a paper called GNN Explainer that sort of capitalizes on the thing that I was mentioning before, where you sort of know the context that the network is looking in when it's making a prediction. So I haven't played around with that much, but I know it exists. But that would be sort of the path that I was going with as far as explainability for neural networks on that slide.
All right, thank you. And here's another one. So they say, very interesting as a MD, I wonder if you can represent all medical records for each patient to predict some pathologies or drug treatments. Do you have thoughts on that?
Yeah, so right now we've been mostly dealing with these embeddings for patient similarity. And that sort of goes along with predicting, you know, pathologies or drug treatments if a patient is similar to a patient that had success with those things. You know, that might be a way to narrow down the scope of the things that you might want to try or things like that.
And then we just have a general question about temporal data. Would you add that as dates, as properties on the edge, or what would your suggestion be?
So in this data set, in the schema that is posted, I do have dates on the edges. Haven't incorporated temporal data yet, quite yet, but certainly something that I'm exploring. And yes, I put it on the edges.
All right, and we have another one. Could the algos for predicting edges work for a pair of edges that have no path between them?
Could the algorithm for yeah? So so if you have embeddings for every vertex in your graph, let's say you sample 70% of your edges are going to be training. 70% of your edges are going to be training edges, and 30% are going to be testing edges. And so if you have a representation for every vertex, you can then like concatenate those two vectors together. And so those would be your features into the machine learning model, probably a neural network, just because those tend to work better with embeddings. And then your label would be if those two vertices have an edge between them. And so if you predict, if you have your two vectors concatenated, and if there's an edge or not an edge, that becomes your training set that you train your model on. And then you can concatenate any two vectors vertex embeddings together and predict if there's an edge between them.
Okay, and then we have a lot of temporal questions. Temporal data, can we go deeper into temporal data, geospatial applications? We have questions related to temporal graphs and modeling time. There are other Graph Guru sessions that specifically talk about temporal data and modeling time in that, but we can include some links as well, since there's quite a few people asking about temporal data. Do you have any general thoughts that you want to talk about as temporal data, besides just labeling on the edge, but as it relates to maybe embeddings with time?
Yeah. So one of the papers that I'm currently looking at is out of Walmart Labs. When we're done, I'll make sure that TigerGraph gets the link to it, and can blast it out to everybody. But they were using it, I believe, for product prediction, where, maybe a customer buys diapers for a year or 2 or 3 or whatever. But after a certain amount of time, that customer is going to stop buying diapers. And that type of temporal data where, things start and stop is important in a lot of different time aspects, or in a lot of different fields. Walmart having their uses. Another paper from Twitter called the TGN, I believe, was predicting if, I believe it was predicting when people would follow each other. I don't remember exactly on that data set what it was, but lots of different use cases. Like I said, in the medical field, it's, something 5 years ago, unless it's a recurring, chronic disease, it probably doesn't matter, things like that.
Okay, and then there's one more, but I'm unsure if there's a question related to it. I'll just read it verbatim. For medical treatments like drugs, my preference as an individual, not an MD, would be to use a tailored approach based on generic metabolism assessment of individual patients. So it's not necessarily a question, but it's a statement. Do you have any thoughts on that?
Yeah, I mean, this is all very R&D work that we've been doing. Obviously, your doctor is going to be your best, chance, or we're not here to replace your doctor as far as recommendations. Obviously, that would be there would be a lot of risks running, relatively black box models to influence somebody's health. Not very ethical either, but something to maybe jog a doctor's mind about this drug or that drug. Something to assist the doctor, not necessarily replace them. And that we don't have any genetic information, because we don't. That's costly still somewhat, and very cutting edge research. So there's a long way to go on that type of stuff. But
all right. Well, it looks, I was just going to say there's no more questions, but a few just popped up. So I guess we have a few more minutes. So let me look at the questions here. Are there different algorithms that we need to use, or could we apply the same ones? What if edges and relationships need to be represented in continuous space rather than discrete one? Are there different algorithms we need to use?
What if edges relations need to be? So I'm not entirely sure what you're getting at there. I think if your edges and relations, I mean, your edges and relations end up as embeddings as well, which would be in a continuous vector space. But if you wanted to elaborate on that, I'm not entirely sure what you're getting at there.
All right. I think we'll wrap this up. If you have follow-up questions, feel free to reach out to Parker Erickson or myself or Tiger Graph, either one, and we can help you out. Again, Parker's link for his LinkedIn is right there. So if you type in Parker Erickson or send him an email at parkererickson30@gmail.com. Do you have any closing, David?
Yeah, sure.
Oh.
Thanks. Thank you, Parker. I'll echo what a few people have been saying in chat. That was an awesome presentation. And thank you, John, for moderating the Q&A section. And thank you to our attendees for joining us. We hope you found this to be both interesting and informative. And we will email the slides. A few people were asking about that. We'll email the slides shortly after the webinar concludes. The marketing team here is quite prompt. And I will also share the code and so forth. And also, last thing from me, we do these webinars, these Graph Gurus webinars weekly, at least weekly. So please keep an eye on our webpage where you can sign up for future events. Or if you're already on our emailing list, you'll get notifications about next week's events and the weeks following. So with that, wanted to thank everyone for attending. Great job, Parker. Great job, John. And thank you for attendees. And we'll see you next time.